So my name is Jake White, and my white paper is on the differences between focusing light from LEDs using CO39 lenses and mirrors for the purpose of illuminating objects for vision systems in industry. So to get started, objects need to be illuminated evenly with light for vision systems to work. So if an object is poorly lit, then then the camera can't identify any problems with it, and uh, it won't work properly. If an object is too brightly lit, then the camera is saturated, and the object won't be able to identify any differences to classify the object properly. Um, if the light is unevenly distributed, so you might have some parts fine, some parts too dark, or some parts too bright, then again, you're going to have the same problem. You need the light to be evenly distributed at the right level across the entire object. So the light I'm going to be talking about will be coming from LEDs. These are cheap and efficient ways to light up an object. There's other ways like laser, but I'm going to be talking about LEDs here. But the problem is these don't distribute light evenly. The light is spread out at an uneven distribution, most of the light is primarily focused in the single direction where it's pointing. And as you go out, it decreases in intensity. Okay, lenses or mirrors can be used to correct this distribution of light. LEDs also have comes in different shapes and sizes depending on the manufacturer and the wavelength and other things that we talk about. So here's an example of what you don't want. Here you have on the left the object you want to have a look at. We'll call it a potato. And on the right, you have the red circle, which is the LED, and the camera above it. And the light coming from the LED is unevenly distributed. Most of it is in the center because the LED is pointed towards the object. But then some of the light, only a small amount goes to the sides, which means the sides of the potato won't be illuminated as brightly as the center. So the camera, what that sees is it will see the sides of the potato might be poorly illuminated and won't be able to make out any features that it can use to classify it properly, while the middle of it, the potato might be too bright and it won't be able to make out any features properly, or it might be fine. It's just uneven distribution of light is not good. So what you want instead is the light to be evenly distributed across the entire object. This is done using lenses or mirrors. Lenses are placed between the object and the LED, and the LED then emits the light, and the light bends as it goes through the lens and is redistributed to be dispersed, distributed evenly across the entire object. The other way to do this with mirrors is have the mirror on the far side of the LED away from the object, and the light then will be shone towards the mirror and then reflected off the mirror to go back towards the object, illuminating it evenly. So a bit about LEDs is that they stand for light emitting diodes, and they can emit light at all wavelengths, at multiple wavelengths that you want. So like you can have a LED at 480 nanometers, for example, which is bluish, or you could have it in the infrared range, or you could have it at the ultraviolet range, and it will just emit light in that wavelength. And the other advantages of LEDs are, as I said earlier, they're efficient because they use low amounts of power compared to like your incandescent light bulbs, and they are cheap to manufacture. As I said earlier, they distribute light unevenly. You can see that in the center graph at the top. You have two grids. They're both actually the same thing. It's intensity with angle. On the right half, you just have the angle in a regular grid with the angle on the bottom and the intensity along the y-axis. But on the left, you have it actually like as a radial grid, so you can see the actual angle. So as you can see, if you're looking at the LED straight on, it's brightest, but as you go around to the side, it's darker and darker and darker, and behind the LED, there's no light because the light's blocked by the physical components of the LED. And then you also have LEDs, as I said, come in different shapes and sizes. So if you look at the two LEDs at the bottom, one of them has a larger bubble than the other, as well as just different shape inside the actual bubble. And this can mean that the center of the light, the origin of light in the LED can be at a different location, causing issues with similar to having different focal lengths or points on a lens, so the light won't be distributed properly. Also, the casing can also be different. So what here, the white square are roughly the same size, but they could also be thicker or smaller, and just a bunch of different issues that means that you kind of have to compromise on the shape of your lens and placement of your LEDs so that you get as good across the entire board as possible. So how lenses work is they change the speed of light as they enter through a medium. Then the velocity changes, and this change in velocity, so when the velocity changes, it causes a change in angle, causing the light to bend, which is where the light bends. This bending of light is called refraction. Refraction can use, refraction, how much something refracts is called the refractive index and changes based on each wavelength. So red will have a different refractive index than blue light, for example. This also happens with infrared and ultraviolet light, which is used in industry because it can allow you to see certain things for some materials that visible light just won't let you see. This causes issues when focusing light on multiple wavelengths and is called chromatic aberration. So this is where red light, for example, red light, for example, would bend and focus towards one point, and blue light would bend and focus to another point as it passed through a lens. So when working with LEDs, it's the reverse. You aren't focusing light, you're dispersing light from the focal point. So you'll have all the red light and blue light, for example, hit the lens at the same point from the LED, but then it won't be dispersed as evenly. And this will mean that some parts may not be illuminated by blue light, for example, or it may be illuminated by, well, it won't be illuminated by red light, or maybe the red light is dispersed to at a more wider range than the blue light. Meaning that your red is really dark, and these are issues that you don't want. So another issue with CO39 is it absorbs some wavelengths of light. So this material allows visible light to pass through easily. It's used for making glasses that people use to see, and that means that but what it doesn't allow much of is ultraviolet or infrared light to pass through. This means that this doesn't matter for people because we don't see ultraviolet or infrared light, but it matters for classification of objects using vision systems, which do use it or can use infrared and ultraviolet light, because that means that if the light gets absorbed by the lens, then a lot of the light gets absorbed by the lens, then you won't get a lot of light coming out of the lens. So you might have a bright infrared LED going into the lens, but it could be really dark leaving, and that means that the camera might not see anything at a bright enough level to actually make any decisions on if something is good or not. It can't identify it properly. Similarly, it would be the same for ultraviolet. So one of my papers I did literature review on looked at the study so it looked at the difference in absorption for ultraviolet and visible wavelengths at different when putting CO39 at different temperatures. So on the x-axis here, you have the wavelength in nanometers, and on the y-axis, you have the absorption coefficient, which is how much light got absorbed. So as you can see, the wavelengths in the visible spectrum didn't get absorbed as much as the wavelengths in the infrared spectrum, and also increasing the temperature you had your CO39 at increased the temperature, so increase the amount of absorption that happened. So you want to have your CO39 at as low a temperature as possible, but it's still a huge amount of absorption from UV light, which is not ideal. So on to how mirrors work. So mirrors, an object has a reflective, so mirrors are an object that has a reflective coating applied to it to allow light to bounce off it. Light reflects off the surface in a consistent manner that is the same for all wavelengths. This is different to lenses which have a refractive index for each and every wavelength. So there is no chromatic aberration with with mirrors. So how mirrors reflect light? You have your reflective object, which is the black line on the bottom, and you have your light going in on the left. It comes in at an angle measured to the normal or perpendicular of a point of the uh, reflective surface. The angle measured is I, known as I, the angle of incidence. And when it bounces off, you measure the angle that's reflected from the normal. It's the angle of reflection. They are both the same. The angle of incidence is equal to the angle of reflection. This makes it really easy to calculate how much, where any light will go when reflected off an object. So this can be used by making mirrors parabolic in shape. This is where, so what happens here is all horizontal light coming into this parabolic mirror will bounce off the mirror and then end up focused at one singular point called the focal point. And this can be used so if we were to use this with an LED, for example, you can see instead of we will reverse everything. So now instead of receiving light at the focal point, we're sending light from the focal point. The LED sends light out, it hits the reflector, and then bounces out horizontally, evenly ideally evenly distributed. Unfortunately, as we talked about earlier, the intensity of light changes with the angle of the LED. So that would mean that you'll have more light coming directly from the LED where it's facing, and less light at the edges of the LED, which means that you won't have even distribution of light. This can be corrected for by changing the shape of the mirror slightly. Also, you can only use half of the parabolic mirror because the other half will be blocked by the LED and the circuit board is on, of course. But that's an easy workaround, just add another on the other side. So in conclusion, lenses are not ideal for distributing all wavelengths of light. Mirrors are ideal for distributing all wavelengths of light, on the other hand, because they don't have chromatic aberration, and they don't have any refractive index or absorption problems, or as much as CO39 does. Infrared and ultraviolet light are used in industry and are important. They're important if they the fact that they are used tells you how important they are, because some materials are easily identified using these wavelengths. Having clear infrared and ultraviolet images greatly increases classification because of that. So if you have objects that aren't classified properly, that because you aren't getting enough ultraviolet infrared light, you're going to have problems against your competitors. And that's about it. Thanks for watching.